All right, this is a demo of k8shazgpu. So this is an extension of something called canhazgpu that's been extended to work from a single host to a cluster of hosts using Kubernetes, especially using Kubernetes DRA, which is dynamic resource allocation, which is an API for allocating usually limited, but dynamic resources on hosts and totally built for GPUs. So I took the idea of canhazgpu and I extended it with a vLLM specific band. And I'd like to give you a quick tour of that. And I'm going to start by showing you canhazgpu itself. So this is a tool that my buddy Russell put together, and my team has picked up on using it. And it allows you to run an arbitrary command that's going to allow you to reserve a particular GPU to use. So in my terminal, quick click, we've got kind of two parts. For now, we're going to look at the right side, which is the canhazgpu server. And over here, I've got a developer workstation, and we'll look at that in just a few minutes. But for now, we're on the server. And we can see that it's got just a single lonely GPU here in my home lab. So what we're going to do is we're going to call canhazgpu to run arbitrary command. This is just a demo script that's going to run and use a little bit of memory on this card. So if we look at the canhazgpu status, it's going to show that my user dev has reserved GPU 0 running this command, and we're using some memory right now. And if I end the command, then it immediately comes available. If you're on a host that would typically be more GPUs, this is real handy. You can say one is available and another is not. Right now, canhazgpu works for one box, and that's essentially its scope. I don't believe it has any type of queuing type features, but once we extend this to a cluster paradigm, we're going to see that we have that kind of capability. So let's take a quick tour here, and we're going to see that we've got a small k8s cluster here. This machine, dev GPU k8s, is the one and only node for this Kubernetes cluster. On that cluster is running some particular DRA driver and Kubernetes controllers to manage a number of aspects to allow this allocation to happen across the cluster. So now that we've kind of got that basis down, let's go ahead and run a demo from a developer perspective. So let's say that I am a vLLM developer and I'm sitting here with my Git clone, and it's of vLLM. It's on my fork of vLLM, and I've made some modifications to it. So I have made one. I'm going to start this the way that one way, and let's look at that diff again. And we're going to see that I've got added just a little bit of code that we can see we've made a modification to vLLM. So now I'm a vLLM developer. I want to go and test my change. Well, typically I'd have to have done that on the server itself and then run canhazgpu and all of that. What if I'm just on my workstation and I want to say, hey, let's run this vLLM? So what I'm going to do is I'm going to use a command that's going to allow me to deploy vLLM with my modifications here. So if I do, I'm gonna say k8shazgpu vLLM run. We're gonna name it instance 1. We're gonna follow the results to it, and we're saying vLLM serve this tiny model for demo purposes. Once I hit go, it is going to do a whole lot of magic for me, and you're going to see a whole bunch of verbose output that we will look at in detail later. But as for now, we can see here that we have .vLM about to run for us. And on the right, we can see that it is in use by the canhazgpu status, our single GPU that we have available. And already we can see that the output that we are looking for, enjoy your noodle soup, is in fact there. So we've run our change, and that has happened on a remote host. So back from the server side, you're going to see behind the scenes, there is going to be a pod that is running which is where GPU has allocated a pod for you automatically. You don't have to do anything. And in fact, canhazgpu is also handling a kind of cache of the resources involved. So for now, that involves a cache of your Git repo, a cache of the base image that you're going to use and apply the changes from your checkout over, and lastly, your model cache as well. So let's take a look at this now from a queuing perspective. So now if we take a look at our k8shazgpu status, we're going to see that we have here one workload allocated on our single lonely GPU, instance one. So if I go and make a different change, so I'm going to make a div, and I'm going to now say when the application loads, hello, dude. And we want to see that run, right? So let's go ahead and do another k8shazgpu vLLM run. It's all good. We're just going to call it instance 2. So I'm going to say, hey, go ahead and run this. It's going to see that there are no GPUs currently available. It gives you a little bit of a grace period to see if one gets released, and then it lets you know that your request is queued. So if I click the status, I'm going to see that currently we have instance 1 pending, our instance 1 running, instance 2 is pending, and as soon as a GPU becomes available, we'll be able to see instance 2 spin right up for us. So let's do that. I'm going to say k8shGPU cleanup in instance 1. We're going to watch the status. This will come out of pending, and we should see pod spin up for us here. All right, and we got our allocation. In that case, it was a little slower than I expected, but we've got the pod up and running. And what I can do now is say k8shGPU logs, and it's going to go ahead and follow the logs from that running pod, and we will see our hello dude here and validate that our changes were run. Interestingly enough, this type of functionality is actually cross-compatible with canhazgpu itself because it uses canhazgpu as a basis and as a source of truth. Canhazgpu has a bunch of great features that handle stuff like having a heartbeat and processes when that heartbeat doesn't come along. So let's go ahead and just take a quick look at that kind of integration. So if I'm going to go ahead and clean up this resource first, and we'll look at the canhazgpu status, and everything should be clear. Now, if I go over to the server side and I'm going to run my demo script again, we're going to see that this is in use by my user dev here on the right. And let's go ahead and create a third instance. So running instance 3, and we're going to see nothing's available, so the request is queued. So let's now watch the k8shazgpu status. Instance 3 is pending. If I go and, if I go ahead and finish this command, it's going to release the GPU, and then instance 3 should be able to come online here in a second. All right, and instance 3 has been allocated, and now I can follow the logs from it. All right, and there's our modification that says, hello, dude. And that is a quick tutorial of the basics, or a quick demo, I should say, of the basics surrounding k8shazgpu. For interest's sake, I'm going to show you a little bit more beyond this, which is to show that there's actually a bit of a system here that backs this, which is this idea of having some things ready in a cache in order to quickly spin up your changes on vLLM. So if I do vLLM or k8shazgpu cache plan show, we're going to see that I have a set of items that can be cached by our kind of backing server here, this Kubernetes controller that we built that knows about these kind of resources. So we have 3 type of things: images, models, and Git repos. Most importantly are really the Git repos and images, because this is kind of how we orchestrate this like quick launch of a vLLM instance. What vLLM is doing, or k8shazgpu is doing with vLLM in the background, is it is going and finding in your repo the latest the lowest common ancestor with main off of your branch, and then it's going and pulling an image that's associated that's built on each CI run. After a commit goes into main, an image is built with this commitish as the tag. Now, granted, yes, this is only kind of a phase 1 here, and this doesn't account for the fact that you could have made wheel changes or changes that require your wheels to be recompiled, say you dipped into the C sources, etc. That's kind of a phase 2 of this particular experiment, if you will. And also I am using some kind of concepts that I have learned from interacting with the vLLM CI SIG as part of the maintainers of vLLM. So we're trying to speed up our kind of CI runs, which use Docker. And I came up with this idea of kind of overlaying your checkout over a pre-built image when it's applicable. That is, when you don't have to rebuild your wheels for vLLM. So in this particular case, k8shazgpu will look at your vLLM repo. It'll figure out which branch and fork you're operating on. It will then go add that to the cache so that those changes are already hot. It'll figure out what your diff is, and it will pack that diff onto into the running image as well. So like if I do a git status here, I can see that I've got this change to init.py, and I've also got a banner text. What's not shown here is that I also touched a file, and I'm going to show you that in a second, because I can actually do a k8shazgpu debug. It's going to drop me right into this container, and I'm going to see my repo as I left it. So for example, I've got this new file called parse file that I just wrote foo in, but that's already there because it's part of my changes on my branch. But then it's also got my diff in there too. I'm not sure if there's actually that is the wrong way to look at it. Yeah. I think that's the one. I have gone ahead and messed up my terminal. So let's just think about that for now. But regardless, my diff is in here, and I didn't prepare for that part of the demo, but we can go in and interact with that as well. So thanks for sticking through to the end. I appreciate it. And yeah, just a bit of a proof of concept and an experiment that I'm looking at. And thanks for taking the time. Appreciate it.